Welcome to this explainer. Every single time you board a commercial flight, you're basically placing your life in the hands of this incredibly rigorous but totally invisible system operating at 30,000 feet. And no, we are not talking about aerodynamics or those massive titanium turbine engines today. We are talking about the code. I want you to ask yourself a pretty stark life or death question. What actually happens if the software fails in an aircraft? We've all had our laptops freeze up, right? Or our smartphone apps crash out of nowhere, and usually it's just a brief annoyance. You reboot and you move on with your day. But up in the sky, an operating system crash isn't just some minor inconvenience. It can trigger immediate, absolutely critical consequences. And that introduces what aerospace engineers like to call the zero fallback problem. Think about it. If your car's software has a critical glitch, you have a safe fallback, right? You just pull over to the side of the road, put the car in park, and safely restart the whole system. But in an aircraft, there is no side of the road. You can't exactly pull over to a cloud and try turning the engines off and on again. These systems absolutely must operate reliably under all conditions because there's simply no fallback. And honestly, this singular, terrifying reality is the driving force behind the immense rigor of aviation software development. So, the strict rulebook governing this entire reality is called DO-178C. This is the big one. It's the widely recognized de facto global standard for airborne software used by aviation authorities all over the world. It defines exactly how software has to be developed, verified, and documented. And when we say software in this context, we don't just mean those cool graphical displays you see in the cockpit. It encompasses all executable code, the operating systems embedded deep in the computers, and even the static data that those programs use. Literally, all of it falls under this massive, uncompromising umbrella. There's really a fundamental principle at play here, which is that aircraft software is something you can't see and you can't touch. Yet it must be treated with the exact same care and consideration as a physical aircraft part. We all naturally understand that a physical titanium jet engine turbine requires rigorous safety checks. Well, just like that hardware, those invisible lines of code managing the engine demand the exact same level of uncompromising rigor. To handle this, the aviation industry manages things through what is basically a strict matrix of catastrophe. It outlines 5 specific levels of software failure, graded from level A all the way down to level E, based entirely on the potential impact. Level A is the absolute most critical. We're talking catastrophic consequences here, aircraft loss or fatalities. Then you move down through hazardous at level B, major at level C, minor at level D, until you finally reach level E. And at level E, a failure essentially has absolutely zero effect on the safety of the aircraft itself. As you might guess, the higher the level, the stricter the engineering requirements. Now, to really put this into perspective, let's map these abstract levels directly into the cockpit. You'll notice that level A governs those hypercritical systems like GPS, the attitude and heading reference systems, and satellite navigation. That code simply has to be flawless. But all the way down at level E, you find systems like the in-flight entertainment. Look, if your movie freezes mid-flight, sure, it's incredibly annoying, but the aircraft isn't going down. This kind of tiering is absolutely crucial because it ensures that aerospace developers are focusing their most extreme rigor precisely where human lives actually depend on it. To truly grasp the extreme rigor of that level A software, just consider the math for a second. Less than 10 to the power of -9. That is the acceptable likelihood of a catastrophic software failure per flight hour. To put that into plain English, it's effectively demanding a failure rate of less than 1 in a billion flight hours. 1 in a billion? A failure must be almost completely inconceivable. Achieving a number that practically rounds to zero like that, it's a monumental engineering feat, and it requires an absolutely flawless process. And achieving a failure rate that practically rounds to zero requires a highly regimented development lifecycle. Under DO-178C, it all kicks off with strict requirements, detailing exactly what the system's behavior must be. After that comes the design of the software architecture, which is then followed by the actual implementation, or the coding itself. Finally, everything undergoes absolutely exhaustive verification. But you know what the real secret sauce is here? Traceability. Every single step, every single artifact must be unequivocally connected. The requirements trace to the design traces to the code, and the code connects directly to the verification tests. Seriously, if even a single line of code exists without a traceable requirement, the whole thing cannot be certified. No exceptions. Now, with a process this incredibly intense, you can imagine a lot of myths pop up that we really need to debunk. First off, people often think testing alone is sufficient. Well, that is wildly false. In aviation, testing is really just one part of verification. You also need deep, independent reviews and structural architectural analysis. Second, some folks think documentation is just bureaucratic red tape. False again. Under DO-178C, documentation isn't some mere formality. It is the essential, hard evidence required to actually prove to the authorities that your system is safe. And third, people naturally assume this is only for massive commercial airliners. Also completely false. This level of rigor applies to a massive range of aviation systems, both large and small. Verification has to be baked into the entire process from day one, not just tacked on at the end as some kind of afterthought. To really anchor this whole concept, let's contrast it for a second with automotive engineering, specifically a standard called ISO 26262. Now, both standards obviously share the ultimate goal of ensuring safe system behavior, but their core philosophies really reflect their drastically different domains. You see, DO-178C for aviation is strongly evidence-based. It is obsessively focused on strict software certification, proving unequivocally that the code behaves correctly under literally all possible conditions. On the flip side, ISO 26262, the one used in cars, well, it tends to be a bit more process-oriented. It focuses more broadly on the functional safety lifecycle. It's a fundamental philosophical difference, and it is driven entirely by that zero fallback reality in the sky we talked about earlier.
As you can probably guess, all of this uncompromising rigor absolutely does not come easily, and it certainly doesn't come cheaply. Meeting DO-178C goals presents monumental real-world challenges. Engineering teams are constantly having to balance the immense effort of required documentation, super long development times, and that strict need for independent verification. In fact, for Level A criticality, the verification actually has to be performed by entirely separate engineering teams just to eliminate any possibility of bias. Honestly, getting a project out the door while absorbing the massive cost and complexity of these safety expectations, it is arguably the single greatest challenge in the entire aerospace industry today.
So think about it. Next time you're sitting in a window seat just looking out at the clouds, remember that you are totally reliant on a computer to keep that plane in the air. If your life depends on invisible code at 30,000 feet, wouldn't you want it tested to the point of near impossibility? I know I sure would. The next time you fly, just take a brief moment to appreciate the hidden extreme rigor of DO-78C. It really is the invisible safety net making modern aviation the safest form of travel in human history.